In this video, I'm going to be talking about one of the examples in Principles of Physics, example 1.8. This is on page 21. I am actually going to be extending it, so you need to read and understand that example before viewing the video if you're going to get anything out of it. So in that video, we have a hiker who starts at the origin, travels first to a point here, travels then to a point here, and ends up with a resultant vector here. And the question calculates components and figures out how the hiker would get back from there to the origin. The components are given by here, and I'm just going to copy down from the textbook. So the first vector is A, components are given here, and the second vector is B, components are given here. Notice that the A vector has the same magnitude for both of the components. That's because the angle here, right here, is 45 degrees, and so the components will be the same. So let me get rid of those. In the original problem, the vector B, the hiker traveled 60 degrees north of east. What I want is the hiker to get confused and go 60 degrees south of west and see where they end up. So what I need is I'm going to go 60 degrees in the opposite direction, so I'm going to be going directly opposite his original direction. And so right here is going to be 60 degrees. And the resultant vector is now something along the lines of that. So I'm going to call that the original vector. I'm going to call it R. I'm going to call our new resultant vector R prime. So the first thing we want is to be able to is to know what this vector is, this new vector. So originally, this vector was B, and this new vector is the same length as the original, except just in the opposite direction. So that means that it is negative B vector. So the original resultant here was vector A plus vector B. Now I want vector A plus minus B, and so I can write the new resultant as vector A plus minus B, which is minus B. You can write that in terms of components, like that. And by using the components which I wrote down earlier, we can find the actual value for this vector, and it's negative 2.3 I minus 52.3 J. And then I'm just putting the units on the outside to make the notation a little cleaner. So if I want to find the magnitude and the direction of this new vector, I can find the magnitude easily enough with the Pythagorean theorem. And this comes out to be something like 52.35 kilometers. And you can see that that total magnitude is very close to the y component of the resultant vector, and that's just because the y component is right here and the resultant is right here, and they're very close in size. So now I want to find the angle of this vector, but that's a little bit more complicated because I have all these things going on. And so what I'm going to do is I'm going to redraw the triangle which is formed by this vector. And I'll show you how I'm going to do that. First I'm going to move this to give myself a little more room. And this new triangle is going to be, this is the y component of the resultant vector, this is the resultant vector itself, and this is the x component. So this is our y prime, our x prime, and r prime. So I need to be a little bit careful here. This is now a vector. These lengths are real positive lengths, whereas the components for these guys are negative because this is in the negative y direction, this is in the negative x direction. So actually when I write this triangle, what I really mean are the magnitudes of each of these components. So now I can use my knowledge of trig, and I have an opposite angle, I have an adjacent angle, and so I can find this guy, which I'm going to call alpha, by taking a tangent of alpha is rx prime magnitude divided by ry prime. And if I just work that out, I can get the answer, which turns out to be 2.52 degrees. So that's good, but it doesn't really relate back up to the original diagram. the angle here is, this is the southern direction, and that's the western direction. The angle is moving from the southern to the western direction. So this angle is 2.52 degrees west of south. And that tells me what it is relative to the original. Right up here. So now this illustrates one of the possible complications that students encounter when dealing with this kind of problem. So usually, or sometimes, you may think tangent of an angle, and you have this picture here, this triangle in your head, and you think, oh, tangent of that angle is y over x. But you see, in this case, that wasn't true. This was the x component over the y component, not the y component over the x component. And in fact, if you had done this problem like that, done it incorrectly, and put our y over our x primes, you would have found that theta is something like 87.48 degrees. And so you'll notice that this and this add up to be 90 degrees. And that's essentially because you're not finding the angle in this little area right here. The angle you're finding is from here to there. And essentially that just comes from exchanging the role of the x and the y components. So the lesson here is that if you need to find the angle in this kind of situation outside of the first quadrant, you're in quadrant 2, 3, or 4, it can be a lot safer to just draw the triangle that you have, use your regular SOHCAHTOA type trig knowledge to find the angle, and then figure out from what axis it's relative to. If you need to find it relative to the eastern axis, for instance, then you can just start adding 90 degrees, for instance. You could say, because I need to add 90 here, and then 87.48 here, but you can manage it, you can figure it out. Instead of memorizing all those rules about tangent, sine, and cosine being positive or negative in whatever quadrant it is, just draw the triangle, figure it out, and then relate it back to an axis that you know.